insulation level of the system. For instance, here, the 900 kV. But we could directly specify stroke current, the maximum, the maximum stroke current that the system can safely take. Or you could specify the protection level. Protection level is just basically standard level of physical current. Don't protect again. And you can even go so far as just specify the striking distance. This is more for academic purposes, but some methods will just allow you. So basically, this define the size of the rolling sphere if you're using the rolling sphere method. So often than not, basic impulse level is a good way to specify it. And you can get the parameters regarding this are there. The voltage level, the surge impedance. You can see that in greater detail on the screen here obtained by Moore. So you can specify those parameters to determine the level of current that the system can take. Once you've done all this, you can click process and you get the analysis. Now, what is going on here? We see that after processing this case, we have two little red spots. This indicates that there are parts of the model that are not protected with the current shielding system. I have a little summary here that really says that also. It's not protected. You can see the details. The details in the report. You see it is generated whenever you run, process the model. You get a report that shows everything that was specified in the model. And excuse me. Wait a second. Well, I have some difficulties to find them. In there someplace, we have the list of the objects that were not protected. Okay, right. List of the unprotected model. So it gives you all of the parts of the model that were not correctly protected. So by combining the visuals here, and another way you can visualize this, you go under View, Collection Surface Rendering Steps, and you can ask to make it transparent, so you can see really what is outside, and then underneath it, you can rotate, view, try and get an idea really what could be done to protect it. For instance, here we could move the masts in that direction maybe a little bit, or install new masts here to protect the system. So that's basically what the program has to offer. It's really easy to use. There's one more feature that is actually interesting. Also, the program can calculate the shielding failure rate for any given shielding design. So here we see that it does fail occasionally for that particular lightning current. But you may also ask for it to analyze all types of lightning currents according to a certain probability curve and report how many failures are expected during a typical time span. I don't know here if this is set up to do it right. So we have load the shielding failure analysis setting screen. Go in there. You can specify this is the ground flash density, how many lightning flashes are expected per unit area in the system, and parameters controlling the lightning current distribution, how much the percentage of lightning strokes that have current greater than a certain value. This is a curve that, is specified for now just in terms of its median, the median value of the stroke current, and the exponent. The actual formula, I don't know if we have. This is relatively new, so we may not have the help on that. No. Anyway, the formula may be listed here. No. Okay. No, it's not listed. But anyway, it's a standard formula. We'll have it once it is completed. That gives the form of this curve, and that is normally used for this kind of analysis. And we have other parameters to control how we integrate these whole things. I'm not sure this model here will actually make sense, but if I go under project, analysis, I request shielding failure analysis and process. It takes a little bit more time now because it's analyzing several different current levels and then accumulating all of the failures for all of these levels. But ultimately it's going to tell us just how many failures are expected for the entire site for a given period of time, based on 1 year.
Simone, what does the contour give you? Like, is that the zone of protection? Because typically you're used to seeing that inverted the other way, right? Like
Yeah. This is really the capture zone, if you wish, of the particular object. So now let me just try and see what we actually have that with the knowledge. The graphics here may not be so interesting, but shielding analysis, failure analysis. You see here it summarizes exactly how many failures it found, and the total expected number of failures per year is 3.17 times 10 to the minus 4. That's a relatively small number, so one failure per 3,000 years is relatively well protected. But to go back to the standard analysis mode, just shielding analysis and reprocess it, so we see the picture we had. The parts in red are the collection surfaces associated to the objects to be protected. So the collection surface is really generated by taking the object, the physical object, and basically starting a sphere, basically generating a sphere out of every point on that surface. So that means that each lightning flash that contacts this surface is going to hit that particular object. For one object here, from the visuals, you cannot see where it originated from. You don't know. We don't internally in the program which particular object generated which part of that surface. But what we see is only the combined, surface of all the objects. So, but what can be seen visually then is that there are objects in this area that generated this collection surface that is vulnerable, is not protected. The green is what is generated, the same collection surface, but generated by the equipment, by the shielding system. So whenever the green part is located above the red part, basically, that means that the shielding system is going to intercept lightning. It's going to hit the lightning shielding system before the objects will be protected. So that gives you an indication of that some objects are to be protected, and also gives a direct measure of the level of exposure. So that's the area that is exposed. So that we can know, and that's how we can calculate the failure rate. You multiply that basically by the number of lightning per unit area that is expected that you specify. So, but as I said, it's a little bit difficult still to see which object really generated that. It's listed in the report, and in the future version we will highlight it directly in the drawing. See directly which objects were not protected. So it's going to be a little bit more similar to what you would get in the standard way of displaying, where you can see a part of your object sticking out of the protection area that is generated. So, okay, that's about all I have to say about this program. There are other options. Now, this is the rolling screen. Normally, that's what you use. You can use a protection angle and some other variations on the rolling sphere or the electrogeometric model, the Ericsson method, and also we had the mesh method, which is still used in some cases. And the collection volume method also, which is currently being developed. So if you encounter those methods, they are available.
If you have a residential area, we have more, there's a lot of trees, which are probably can be considered as a good lighting, we can conduct it,
Yeah, well,
can you model this?
you could model trees, of course. It wouldn't necessarily. It's a lot of work to model a tree in all its detail, but you could model it as a few cylinders. It's just a matter of putting the geometry.
I'm relying on a tree because that's the biggest tree is probably going to hit first.
Yeah, well, you could consider it as being part of your protection system. I mean, maybe the tree wouldn't like that, but it's.
But the tree is not a conductor, not a pure, not a good, very good conductor. So
it's not a very good conductor,
yeah.
but it may still intercept lightning. It's basically a valid target compared to. Well, compared to air, it's still a decent conductor. So, from that point of view, it's a valid target for it. So, yeah, you can model it. If you want to account for it, you can put it there, just mention that it is there, and mark it as being ignored. But if you, because normally, it's not a naturally occurring object, you wouldn't necessarily want to mark it as being part of your protection system. You don't know it's going to be there tomorrow. But anyway, if you want to see its influence on the system, you can see it as an object to be protected, or as an object part of the protection system, or just leave it there as a decoration. Any other question?
Does this have anything to do with BIL levels?
It does.
Or so if you have different voltage levels with different BIL levels?
Right. For different BIL levels, presently what we do is we do the analysis twice.
Okay.
So that's about it. We do the at the two levels. We're currently working on making it in a single analysis, which is just more convenient. Because normally, in most substations, you'll have two levels. You have a high and a low voltage level. Okay. Or at least two, it could be even more. And so, anyway, that will simplify things. But right now, and in fact, it may actually make it more correct in some ways. Because when you do it now, you'll do it in two separate analyses. But when doing, say, the high voltage part, well, basically, when you do the low voltage part, the high voltage kind of protects it. Right? It can act, you can effectively consider it this way. And so, anyway, once we have the fully integrated method of doing this, it's going to account for all of these and give you options. But now, it's your decision. Okay. Once you have once you model the low voltage, you can say, okay, the high voltage, completely acts as a protection for it up to a point.